So in previous lecture, what we have been focusing on is basically focus on the bending normal stress at the root location. Okay? So essentially, that failure due to bending normal stress, okay, and which is this location, right? Yeah. What we did is we derived a so-called Lewis equation. The Lewis equation is an equation. It's a stress value. Basically, it's an equation representing the stress at the root location at here. So that's a Lewis equation, very original equation for calculating the stress at the root here. Inside this equation here, the WT is the transmitted load, which is a horizontal force. Capital P is the diametral pitch. Okay? F is the phase width, and the Y at here is called Lewis form factor. So Y at here is equal to 2x times capital P and divided by 3. So which is basically called Lewis form factor. It's a factor that's closely related to the form of the tooth at here, okay, of the gear tooth. Okay. So there are a number of things that are here. I wanted to point it out. Okay, basically. So if you look at this equation, Lewis equation here, some very simple observations. Okay, so let's say, okay, if the number of teeth, capital N, okay, not changing. Okay, if you keep the number of teeth as a constant, and then we change this. We change this diametral pitch P. Okay, we change this diametral pitch P at here. Okay, yeah. So I'll show you a animations in here as this. Okay, so here in this software here, you can see basically the diametral pitch is over here. This is diametral pitch, and the number of teeth is over here. Okay, the number of teeth is over here. The top one is the gear, and the bottom one is the pinion. All right, yeah. So let's blow it up. Let's look at the pinion gear tooth. Okay, let's look at the pinion gear tooth. So I'm gonna explode it a little bigger. So here's a pinion gear tooth, right? Yeah. So now I want you to observe this gear tooth profile, right? And while I'm changing the diametral pitch value here. So let's see if I change to, let's see, 12. Okay. Let's maybe just plugging back over here. Okay, well, observe the tooth profile. If I change to this is 12. Here's a 10. Okay. Did you see any? Just look at the geometric shape right here. Would you see any change right here? To 8. Okay, the size does change a little bit, but just look at the form, right? The form of the geometric form of the tooth that are here. There's no change, isn't it, right? There's no change. If you change this, just diametric pitch to different values, you can try. And there's no change here. So if you recall that basically the horizontal line go here? Good, it comes back. So this y value at here, okay, this y value here, it's a form factor. So if that form not change here, so this y, there won't be any change. Okay, the y here will not have any change. So the y here, you see that's 2x times p over 3. So this directly related to the format. This format here, right? The geometrical form. If there's no change in the geometrical form, then the y value will not change, basically. Okay? Yeah. So that's one relationship in terms of n, p, and y at here. Okay? However, okay, what you do is if p is constant, okay, if p is constant, and then you increase n, for example, if you increase the number of teeth, okay, if you increase the number of teeth at here. So let's take a look at this one here. Take a look at this. So I'm not going to change the diametric pitch. I will change this number of teeth at here. Okay. So let's see if I change the number of teeth. Now observe that red, the pinning one here. You see that? See that? The bottom there. So maybe a little more here. Okay, so this maximum is between 8, so let's give it a little bigger here. So you see what happens is the bottom of the teeth, right? See the teeth value here? The bottom of the teeth started to what? To expand, exactly, right? So that basically means there is a geometric form change in the gear tooth, okay? And that resulted in the change in this y value at here, right? So if you can imagine the tooth, end of the tooth here started to become wider, okay? Start wider here, and that x value actually will become bigger, okay? So p is not changing, so the capital Y value will actually increase, okay? Will actually increase. So what does that mean? Well, you look at the stress calculation. The y's happen to be on the what? Denominator, okay? So if the y is increasing, then the stress value at the root location should be expected to decrease, right? Decrease. So basically, sigma will decrease here. And that's something you need to bear in mind, especially when you design gear. How do you minimize the stress? If somehow the gear design is not satisfying the requirements, chances are too high of stress, then how do you decrease the stress then, right? Increasing the number of teeth is one way to decrease the stress, okay, at the root location. Okay, does that make sense? So that's one simple example here, okay? Yeah. Now, the figure, table 14-2, okay, covers pressure angle of 20, okay, and then the Lewis form value y corresponding to a different number of teeth at here. As you can see, as the number of teeth is increasing, the y value is increasing at here, right? Okay. So that's basically the Lewis equation there. Before we move on here, we also need to point out basically there are some limitations or assumptions for Lewis equation. Okay. So the way Lewis equation is derived, okay, what's the limitation? I think I mentioned in the during the process of the derivation. We only considered the transmitted load Wt. The other load, the radial load Wr, okay, is neglected. Okay. So the neglect of Wr doesn't necessarily mean it's a bad thing, actually, because Wt generates a bending normal stress, a stretch level, and Wr generates a compressive normal stress, right? So by neglecting Wr, so you're essentially being more conservative. Okay, so which is actually not necessarily a bad thing, but you need to remember this Wr is not being considered when designing for for the Lewis equation, okay, when deriving the Lewis equation. Okay. Another limitation is in Lewis equation, it didn't consider stress concentration. Okay. It didn't consider stress concentration. As a matter of fact, at the time of Lewis equation, the stress concentration concept actually had not been considered yet, because it's a brand new concept basically. It's not coming up yet. So that's one limitation. And the other thing is Lewis equation didn't consider the friction. Okay, so friction is not considered. Okay, yeah. So there are a few other limitations here, but the point here basically is Lewis equation is not the perfect equation. So it's a bare bone equation. So what we need to do is we need to modify the Lewis equation to reflect some of these assumptions, some of these constraints or limitations that's not considered here. Okay, so objective, okay, is to modify this Lewis equation. Okay. There are different ways of modifying it. And for example, right, give you one simple example. The simplest way to modify it is this. You can say, okay, I'm going to introduce a factor called Kv, which is basically dynamic factor, into the Lewis equation. So, like this. So change the Lewis equation by multiplying a dynamic factor Kv at here. So Kv at here is called dynamic factor. Okay. And we'll look at the detailed dynamic factor pretty quickly. So basically, it's a factor by taking this velocity into consideration. Okay? So if you have two gears meshed with each other, then you have this so-called pitch line velocity, right? So that velocity actually will affect the stress level. Okay? At the root location, okay, when the two gears are being meshed together. So the idea is basically, remember, is to modify Lewis equation. Like the handout I'll give it to you, you'll see that there's so many factors we're going to incorporate to modify the Lewis equation here, right? Yeah. Now, ultimately, what we wanted to do is we need to design, right? We need to design for the gear. There are two different approaches. Okay? Two different approach in terms of design for gear. Okay. The first approach is what we call the conventional approach or traditional approach. Okay. So conventional approach. So conventional approach basically means is it makes use of the knowledge that we learned, actually the procedures we learned in previous lectures. Okay. So I'll show you what I mean in here. So for example, right, let's say if you have a gear, basically, let's see, this is not a very good drawing in here, but okay. So let's say if you have a gear in contact with each other. So apparently, there's action-reaction force like this, right? Yeah. And as the motion goes on, if this is probably initial contact point, as the meshing goes on and on, right? So the contact point, moves from here to here to here, and then until disengage, right? Until disengage. So the force, you can imagine the action-reaction force, okay, between the two teeth, basically moves from the beginning, move from the top, and then move to the bottom here, right, until disengage. Okay, yeah. And as the contact point is at the top, then at the root location you have a bending normal stress. As the contact point is over here, then you have another bending normal stress. Over here you have another. So basically, the bending normal stress will also oscillate, right? Will also oscillate. So what you would say is, in this particular case is, you probably will see here is basically the bending moment, start at 0, and then here is your MA. So basically, you will see that the gear 2 experience a bending moment from 0 to a certain magnitude MA, okay, and then come back to 0 like this. Okay, it's like a repeated basically type of loading. Okay. And for this particular one, you have a basically you may have a mean value at here. Okay, yeah. So that's the loading condition for the gear 2 study here. So the conventional one, if you recall that this is some sort of a fluctuating type of loading. So we can calculate sigma A, and we can calculate sigma M. In this case, is actually the same thing. So half of sigma, and then half WT times P over Fy. That's Lewis equation stress, right? And then you can substitute sigma A into the modified Goodman equation, and then calculate safety factor, right? Calculate safety factor. So that's one approach. That's a conventional approach to calculate the safety factor or design using the modified Goodman line, using the magnitude of oscillation and mean value oscillation to do the calculations here. Okay, yeah, that's one approach. Now another approach, which is the approach actually we're going to use for our design, okay, is basically to use the so-called AGMA equation. Okay, so AGMA equation is American Gear Manufacturing Association equation. Okay. It's an equation recommended in AGMA standard. Okay, so it's basically industry standard here. Now this equation here is an empirical equation. Okay, it is an empirical equation. So we're going to use this one here for our design. So I'm not going to dive into the AGMA equation yet, but bottom line is you have the handout right here. So this is basically AGMA equation in your handout here. Okay, yeah. Now for the AGMA equation, take a first look at this. Essentially, it's a modified version of the Lewis equation. You see, you have a WT at here, you have a F. Okay, and then this is not called a Y, but this is called a J at here. You have a diametral pitch, right? So that's a modified version of the Lewis equation, and then a whole bunch of factors over here, right? Yeah. Now that's the one we're going to use for our gear design here. Okay, so I'm going to look at the details for this portion very shortly. Okay, yeah. So this one is where we're going to use here. Okay. Now, up to here, what we have covered, okay, basically are the concepts on normal stress at the root location due to this bending moment, right? Yeah. But I do mention that there's another type of stress or another type of failure, okay, for gear, which is basically the surface failure. So when two gears engage each other, there's constant pressure applied between this pair of gear teeth, okay, and that load, that force, and ultimately will result in the surface failure. Okay, and that's basically the second type of stress we're going to look at here. So we're going to look at the contact stress. Okay, the contact stress. So looking at the contact stress, first step is, so how do we basically model this contact stress, right? Yeah. To model the contact stress, and we use the so-called Hertzing stress model. We use the Hertzing stress model to model the contact stress between a pair of gear teeth. So here is how Hertzing stress derived. So basically, you have two cylinders in contact with each other, and then there's a pressure or force applied trying to compress the two cylinder, right? Yeah. So if you explode the contact area out, so if there's no pressure, it's basically a solid object. It basically is a point contact, right? If there's a pressure, there's a force, then that contact region is not a point anymore. If it's exploded, there's basically a very small flat region, right, due to this compressive force. Okay. So that 2B is the width of the compressive of that region, the width of the being compressed here. Okay. and the diameter of the two cylinders are D1 and a D2. Okay, that's basically the model of the Herzing. And you can derive the model of Herzing. Basically, give us this B at here, which is the width, right? Which is this formula here. Okay, so the maximum pressure is basically force divided by the area. Okay, and then times the length of the basically times the length of the cylinder, give you the area. Okay, so that's the Herzing stress basically. So this one here is essentially Herzing. You don't need to write this down here. Okay. This is basically Herzing stress. So how do we use these results to a pair of gear then, right? A gear tooth. So here's a pair of gear teeth out here. One is pinion, one is the gear. Okay. So what we can do is we can model these two tooth, okay, these two teeth out here as two cylinders. So they're not perfect cylinder, but you can use a certain radius of a circle out here to represent that as two cylinders out here. And the length of the cylinder is basically the face width, right? The face width of the gear tooth. Okay. Yeah. So the cylinder will have a radius, so we can derive the radius at here. Okay, R1 and R2. Okay, based on the pitch diameter radius. So you can basically derive this R1 and R2 accordingly. And the material property for the gear tooth, okay, one is EP, EG, so that's the Young's modular, and VP, VG, that's the Poisson's ratio. So basically, we can make some substitutions, okay, into the existing formula to derive for the contact stress for a pair of a gear teeth set here. So here's the results for Herzing stress. So what we can do is we can see, okay, so here's F, right, in the Herzing stress. We're going to do some replacement. So basically, we're going to do some replacement. Okay, what we can do is, okay, we're going to replace the F with what? With the not WT, with W. Basically, this is the load here, right? This is the pressure angle. that's your W. Okay, that's W, right? And W, if you recall, that is related to the transmitted of WT and also pressure angle. So WT divided by cosine phi, you get your W value here. Okay, yeah. So replace the F with W, okay, and also replace the L at here. The L is the length of the cylinder. So in this case here, we replace that with the face width. So this is a little bit strange in terms of symbol wise, because we use F at here for gear for the face width. So this is not a force, okay? Yeah. But on the other side, this is the force. Okay. And we can replace the D1 and the D2 for the diameter for the cylinder with R1 and R2, okay? And then replace this P max. Okay, the P max is the stress, basically, with what we call it. We call it sigma C. Okay, sigma C here. So that's what we can replace. Yeah. And with this replacement, okay, substitute into this equation over here. Okay, and of course replace the E1 with the EP, E2 with the EG, VP, V1 VP, and V2 become VG. So that equation will become this now. Okay, so you get an equation like this. Okay, yeah. And this equation right here essentially serves as the fundamental equation for calculating the contact stress, okay, or when we design the gear to prevent the surface failure, essentially. Okay, yeah. So this equation right here is called, okay, contact stress equation. So this is the base equation. Okay. Okay, this is the base equation for the contact stress. The R1 and R2 at here. Okay, so R1, R2, right, is the radius. You see this is the radius, the approximate radius of the gear at over here. That can be calculated using the geometric relationship related to the pitch diameter and the pressure angle at here. So you can see that basically R1 is equal to the pitch diameter for the pinion times sine phi over 2, and R2 is the pitch diameter for the gear and divided by 2. Okay, yeah. Okay, so plugging into these formulas, okay, you're gonna get is that good? So I'll jump ahead a little bit here, okay, and we'll derive a little bit. Okay. From this equation, okay, so we can make a little bit of modification in it here. So what modification we can make? So what we can do is let's define, okay, our gear ratio as mg. So we call that mg is ng over np. Okay, that's the gear ratio. And then it's the same as dg over dp. So the pitch diameter for the gear divided by pitch diameter for the pinion. Okay, pinion in here. So you can see this 1 over R1 plus 1 over R2, and R1 is over here, R2 is over here. So the 1 over R1 plus 1 over R2 can be simplified into 2 over dp sine phi, and then mg plus 1 and over mg. Okay, mg over mg here. So that 1 over R1, 1 over 2 can be simplified into this equation. Then I can substitute into the sigma c at here. Okay. So sigma c, the negative sign here, you could neglect the negative sign. The negative sign just means it's a compressive stress, right? So sigma c is just equal to Cp times Wt, okay, over F, okay, times dp, and here's 1 over cosine phi sine phi divided by 2 mg over mg plus 1. Okay, sorry. Yeah, go ahead. This one here? Yeah. No, this is the pitch diameter for the pinion.
Okay, so it is the diameter pitch for the pinion.
No, not diametral pitch. Diametral pitch is capital, right?
Oh.
Yeah. This is the pitch diameter.
Oh, right.
Yeah, pitch diameter. Okay, good. Yeah. So this equation here, and the Cp is still this expression, which is called elastic coefficient. Okay. So this equation here, serving as the basic function, basic expression for the contact stress. Okay, for the contact stress. And this equation is also called Buckingham equation. Okay. It's also called the Buckingham equation. And AGMA, the American Gear Manufacturing Associate, come up with a modified contact stress based on this Buckingham equation. Right? You see, it comes up with a modified equation based on the Lewis one, and then comes with another one based on this Buckingham equation by adding a number of coefficients, okay, into this equation. So as in the handout you can see here. So this is your sigma c for the AGMA equation. AGMA equation, there are a whole bunch of basically parameters over here, right? Yeah. Sorry, where do you go? Here. Whole bunch of parameters over here. But the formality, this dpf, this capital I at here, this guy here is capital I. So this portion, okay, this portion here, as I'll go through this. This is called I here. Okay, this is called I. and that's the surface strength geometry factor. Okay, so we'll look at shortly here. So bottom line is, okay, the AGMA equation is what we're going to use for gear design. And AGMA, there are two basic equations. One equation are for the bending stress. The other equation is for the contact stress. Both equations are modified based on two simple equations. One is the simple Lewis equation, the other is the simple Buckingham equation. Okay? Yeah. By adding a number of factors into these two equations. Right? That's basically AGMA. So if you look at your handouts in the today's handout, right? That's basically what you see it here. Okay? On the first page, there's AGMA bending stress equation for two different type of units, and also AGMA the contact stress for two different type of unit. Okay, and then there's two more equations down there in your first page here. Okay, that two equation basically is the strength equation. So for design, right, as we always do, the simplest approach is to compare stress with what? With strength, right? So you come up with two stresses. Okay, one is bending stress, one is the contact stress. And we will compare the stress with the strength. So this one here are the so-called allowable stress. If the actual stress is lower than the allowable one, then you're safe. Okay, otherwise then it's not safe. That make sense? Yeah. So the rest of the work is basically what we're going to try to figure out is, okay, what are each one of the factors here? How do we, what's the definition for them? How do we calculate each one of the factors, right? And then putting them together, we'll end up with our stress and strength values. Okay? Yeah. So that's basically the rest of the work, to figure out, okay, the definitions for each one of the stress, and also to figure out the values for each one of the factors. Okay? So before we start all the factors that are here, so I want to go through all the factors using an example. Okay? So let's set up the example first, and then we can go through all the factors here. Okay? Yeah. So I will go through example, and at the same time we'll go through all the different factors. So for this example here, let's call it the Spur gear analysis. It's not quite a design one. Okay? It's more of an analysis type of question. So here's a given number of parameters. Okay, diametral pitch. Now, the symbol wise, there's a slightly modification. I used to use capital P for diametral pitch, but just to be consistent, we use a capital PD at it here for diametral pitch. Okay? It doesn't matter. Okay? So, diametral pitch is 6. The number of gear for the number of teeth for gear is 60. The number of gear for the pinion is 22. Pressure angle 20 degree. Okay. Input velocity 1200 RPM. Okay. Input power 15 horsepower. Okay. And we're using gray cast iron. Okay, class 40. And we're going to assume pinion life 10 to the power of 8 number of cycles. Okay. We're going to assume a reliability of 0.9. Okay, so that's all the parameters for this particular question. Okay, so we'll make use of the parameters that are here for our analysis. So basically, here's the parameter, here's the working condition. Analyze the safety of these gears, okay, the pinion, for both the pinion and the gear. So before we dive in, we need to figure out some values first. Okay, yeah. The first value we need to figure out is what is the transmitted load WT. So what does the WT equal to? So we start from torque. Okay. Start from torque. So the question give you is the horsepower, and this is the US unit. So the torque, if you recall the formula relating the horsepower and input velocity here is this formula. So T equal to 63,000 horsepower divided by the revolute per minute. Okay, so the units is all good. And you have 15 horsepower, and then you have 1200 RPM in here. So that gives us a torque which is 787.5. The unit is pound-force inch. Okay, pound-force inch. So that has to be very clear. It's nothing else but pound-force inch. Okay, and then we have the diametral pitch. Okay, and we also have the number of teeth. So I'll be able to derive the pitch diameter for both pinion and the gear. Pitch diameter for pinion is dP equal to nP over the diametral pitch. So that's 22 over 6. It's approximately 3.667 inch. Okay, yeah. So now basically you get here is the pinion diameter, right? Pinion pitch diameter, and then you have your WT applied horizontally, okay, and tangent to the pitch circle. And then guess what? Your WT basically equal to what? The torque divided by half of the diameter, right? Which is the radius. So WT is 430 pound-force. So that's derived. Transmit load WT is derived. So, and if you look at your formula, basically that's the first parameter, right? We need in order to calculate the stress. Okay. Let's open up this AGMA factor here. Okay, so now we got our WT here. We have a whole bunch of other things need to figure out at here, right? Yeah. Okay. All right, let's continue it here. All right, so once we figure out the WT, we have one more parameter we need to figure out, which is the so-called pitch line velocity. So pitch line velocity is a velocity referred to the velocity tangent to velocity essentially at the pitch point. Okay, at the pitch point. So you have a pinion and a gear at here, and then you have a pitch line velocity over here, right? Yeah. So the V is equal to R times omega, okay, and R is half of the pitch line. Pitch diameter for the pinion times omega. So 3.667 divided by 2. But we don't have omega. What we're giving is 1200 RPM. So we need to basically divide it by times 2 pi. Okay, so that's 2 pi readings, right? Per basically every revolute is 2 pi. And then divided by 12 is to convert from inch to feet. Okay, from inch to feet. So this will give us 1152 feet per minute. So that's the standard unit for the pitch line velocity. Okay, has to be in feet per minute, right? In feet per minute. Okay. Okay. So those parameters, okay, are necessary for following calculations, right? And we can stop here, and we can start diving into all the different basically AGMA factors, okay, the factors in the AGMA equation. Okay. So the first one we're going to look at is the so-called KO, okay, and the KO is called overload factor. Okay, it's overload factor here. So that's the KO over here, right? It's KO. So the nice thing is, you see, once we figure out the KO for the AGMA stress equation, we have the same parameter, same variable for the contact stress. So we don't have to do it again, basically. Okay. Yeah. So I'll use my PowerPoint to illustrate some of the concept here. Okay, for each one of the parameters. Okay. So first of all, this is a KO at here. Okay. So what is KO? So you are using a gear basically to transmit the power from one end to the other end, right? Yeah. So you basically have an input power, and then you have the output power. Okay. So like this cartoon showing it here. So sometimes, you know, your input power is smooth. Okay. Sometimes not. And for the output side, and sometimes you have a very large disturbance or low torque. And sometimes it's not, right? Yeah, so that's the different situations here. So if you're using like this kind of a drill at here, so you end up with a lot of shock, right? A lot of shock at the output level, basically. Okay, so that type of basically uniformity at the input and output location will be this compensated by this so-called overload factor KO at here. Okay, yeah, that's KO. So KO is also called surface factor. As you can see, if both of the power sources are uniform, okay, then you basically pick the KO as 1. If you have a situation which has a moderate shock and a light shock, that kind of thing here, right? This is basically the input side, this is the driving side here. Then you use this corresponding 1.5. So that's how you pick up your KO values here. Okay. Yeah. Now, in terms of project, right? The project, I'm not sure how many of you read it. The project is design a gearbox, okay, applicable to a ship industry, basically. Okay, so the gearbox will drive propeller, okay, which is of course will be used under the water, right? So you have the input power side, and then output power side will be within the water, right? So the water, which is inside the ocean, so there got to be some sort of a disturbance there. So the output side will definitely not going to be uniform. That makes sense, right? So when you design for your project, and I didn't specify the KO for you, then you have to specify a KO yourself. Basically, consider the water, the source of this output here, the low torque. Is that going to be a moderate shock? Is it going to be a heavy shock? Right? That's completely up to your judgment, basically. Okay. Yeah. Okay. So that's KO at here. So in my particular case, in this particular example, we didn't really specify what kind of working condition is it. So let's just assume we have a uniform and a uniform situation. So we're going to take our KO to be 1 for this particular case at here. Okay. Okay. So second factor let's look at is the KV. KV is called the dynamic factor. Okay. So KV is the factor over here. That's KV, okay, dynamic factor. And what exactly is dynamic factor then? Right. Okay. Dynamic factor, this is a definition. There's always a noise in the gear, okay? And the noise in the gear is an indication of the dynamic effect. And often in time, the faster it spins, and then the louder the noise is going to be, right? Yeah. If there's a noise, there might be indication there's a transmission error. Okay. So basically, you're not sticking to this uniform angular velocity anymore, right? Using a gear, the whole idea is to maintain the constant angular velocity, right? Yeah. And the source of the error could be many reasons. There could be inaccuracy in manufacturing the gear tooth profile, tooth vibration, dynamic unbalanced rotating members, wear of the teeth, shaft misalignment and deflection, and tooth friction. So this all contribute to this misalignment or producing this effect here. So the kV here basically is a factor trying to take that velocity into consideration, and also take the quality of the gear into consideration. Okay, so this is the formula for kV. There are two different formulas. One is for the US unit, one is for the metric. Okay, so there are two different formulas. Inside the formula, of course, you have the pitch line velocity V, right? Is part of this equation right here. And there's also two constants A and B inside the formula. The A and B equations are given over here. Okay. Particularly A is a function B, and B is a function, another variable called the QV. And QV is called basically a quality factor essentially. It's called the AGMA transmission accuracy level number. It's a quality number. For most of the commercial quality, it takes 3 to 7. For precision quality, it's between 8 and 12. Okay, and that's the relationship for calculating the kV at here. One of the figure in our textbook, which is 14-9, and illustrates the curve kV for different quality numbers. So as you can see, the lower quality it is, okay, you have what? You have basically you have a high for the same pitch line velocity, right? For lower quality, you're going to have a higher kV value here. Higher kV value meaning directly means what? Higher kV basically directly means there will be higher bending normal stress at the base, right? Yeah. So that's relationship. So and also for lower quality level, you have a lower maximum pitch line velocity. At a higher level, you have a higher maximum pitch line. So basically, you can spin faster, essentially. Okay. Yeah. So that's kV here. Okay. So in terms of this question in here, let's say we pick our QV as 8. I wonder if it's given here. Maybe it didn't. Yeah. So let's say we pick our quality to be 8. Now this is also the same thing when you do the design project. You have to pick a quality number QV yourself, right? Typically, you can take if you don't, if you don't spend too much money, then you can use a number in the medium, in the middle somewhere, which is 7 or 8, right? Yeah, that's what I would pick. Okay, so once you pick the QV out of here, then we can calculate our B value, which is 0.25, 12 minus QV, and then to the power of 2 over 3, end up 0.63. And A value is 50 plus 56, and 1 minus B, end up 70.722. Okay. So finally, you use that equation 14-27 for the kV, which is A plus root V over A to the power of B. V we already calculated, okay, which is 1152 feet per minute. So this will give us 1.28 for the dynamic factor kV. Okay, yeah. And now you have the size factor, next one. Okay. Size factor. Size factor, just like marine factor, if you recall that in marine factor, SE equal to Ka times Kb, right? Surface factor, then K surface factor, and then the second one, Kb, is what? It's a size factor, right? It's a size factor. So it's a very similar factor comparing to that. Here's my surface factor here. Over here. So this is the surface factor, the size factor. So it's the factor basically reflects the non-uniformity of material property due to the size. Okay. Typically, this is a value you can typically use in 1, but in my case, okay, in our textbook, we're going to use this equation to calculate the size factor. Okay. So this equation, yeah. So basically, if you recall that when you have SE, basically you have a size factor then times SE prime, right? Yeah. In my lecture notes, I can show you basically the size factor here. It's essentially 1 over that Kb value. It's very, very similar, but it's just 1 over that Kb, because the Kb at here applied to the strength, and the Ks at here is the factor applied to what? To the stress, right? So that's why here is 1 over Kb. So your Ks, okay, we'll use this formula. So 1.192 and F root Y PD 0.0535. We'll use this formula for calculating the size factor here. PD is the diametral pitch, F is the phase width, Y is the Lewis form factor, right? Lewis form factor here. Okay. Now you do get, because Lewis form factor is related to the number of teeth. So for the pinion, you have a 22. So your Y factor for the pinion, okay, will be 0.331. So if you look at the table at the top here for 22, so 22 here is 0.331, right? That's Lewis form factor, right? So that's, and the NG is 60, so then you can get your YG, which is 0.422. Okay. So plugging the YP, YG into this one here, we can get the KS for the pinion, which is 1.091. We can get the KS for the gear, which is 1.098. Oh, by the way, actually, before we do the calculation, there's one more piece of information here we need to use here. So, for this equation here, the phase width. Now, phase width, the question did not specify phase width, right? So we had to determine on a phase width. There is an empirical equation for the phase width, which is this one. So the range of the phase width should be empirically should be between 8 over diametral pitch or 16 over diametral pitch. So that gives us, okay, for this particular question, that gives us a range which is 1.33 to 2.667. And we can conveniently take a integer number 2 inch, okay, for the phase width. And this is something actually when you design for the gear, this is something that you have to make a decision too. You can use this empirical equation, right? Within this range here, you could use 2, you could use the 1.5, you could use 2, you could also use 2.5, right? Yeah. So that's the decision that you have to make here. Okay. So plugging the F, diametral pitch, the Lewis form factor, then you can get the KS value for the pinion and for the gear. Okay, yeah, that's KS. Is that good? Yeah. Okay, so next factor let's look at is the KM, and we call that load distribution factor. So this factor is original formula is a bit of a long here. I'll write down the original formula here, okay, which is in the textbook. It's called CMC, CPF, CPM, CMA CE. So here is the original formula for the KM. Before we define each one of the C parameters that are here, right? Now, what exactly is the load distribution factor here? Okay, load distribution. So you have a pair of gear teeth in contact with each other. Then you have a load basically acting along this pressure lines, right? Pressure lines. Okay. What you really want is you want a uniform basic distribution, but chances are you may not have a uniform distribution, maybe due to different reasons. One of the reasons is because you have the gear sitting on the top of sitting on the shaft. Okay, and it really depends on where you mount the gear. Okay, and there's tends to be a problem with the shaft is what? Deflection. Okay, deflection. So you can imagine, if I have a two-stage for driving, one shaft at here, one shaft at the bottom, and the shaft at here carries the pinion, the shaft at here carries the gear. Okay, and if the gear has a little bit of deflection here, the shaft in the gear has a little bit of deflection, then the mashing of these two will not be actually accurately as it's supposed to be, right? Yeah. So then when it starts to spin, basically the load distribution will not be uniform anymore, essentially. Okay, yeah, that's one of the reasons. Okay, there are different other reasons because there may be inaccurate assembly. Okay, due to the quality of the gear. Okay, this also could cause this load distribution non-uniformity here. Okay, or basically anything that causes misalignment will cause the problem for this load distribution here. Okay. Yeah. So coming back to this equation here. Okay. Now this is not the equation actually we will use, but I'll give you a little bit of quick, a quick story here how it can be simplified here. First of all, this is CPM in here. If you check your handouts, okay. If you check handouts, there is a definition for the CPM. By the way, there is a little bit of modification here. Here on your second page, the symbol says CPM. It actually should be CPF. Okay, you could change that. The pinion proportion modifier is called the CPF, not the CPM. Okay. Yeah. So what the CPM basically is this. Let's say you have a gear sitting on. Let's say you have a shaft supported by two bearings, and then you have a gear over here. If this is the center line of the gear at here, okay, and you have a distance between the center line and the gear, let's call it S1, and then you have a distance, okay, between these two bearings at here, okay, let's call it S at here. So now the CPM formula is this. You will use it as 1 when S1 over S is less than 0.175, and then you use a 1.1 when this is S1 over S is greater than 0.175. Okay, so basically if it's far away from the center line, then your CPM will be 1.1. Okay, yeah. One of the reasons is if it's right in the center line, so at least the slope of the deflection it's flat. But if it's off the center line here, then there is a slope basically, right? There's a slope due to this deflection at here. Okay? And this is, we call this a straddle mounted. Okay? It's like riding a horse. So you mount to the gear or right in the middle between the middle of the two bearings. Okay, that's called straddle mounted here. So that's CPM here. So what in our case we're going to use 1. We're going to assume 1 here. Okay, yeah. And the CMC. Okay, CMC has something to do with the processing of the gear surface. So if it's uncrowned, so basically nothing processed, you use 1. And if this is a crowned, okay, for quantities, and you use 0.8. And again, we're going to use 1 here, okay, for simplicity. So CMC will be 1, CPM will be 1, okay? Yeah. And also, there's another one here in the CE value, okay? CE value here takes also two different things. First, if 0.8, this is for so-called gearing adjusted at assembly, and here is other conditions, okay, and we're going to take 1 again here for the CE value here, okay. So this is 1, this is 1, this is 1, so we're left with 1 plus CPF plus CMA. So your KM here will be left with just 1 plus CPF plus CMA. So then let's look at the details for CPF and the CMA here, okay? Yeah. CPF, CMA. CPF is given called pinion proportion modifier, and CMA is called mesh alignment factor. So I'm going to use my PowerPoint here to illustrate the formula for CPF and CMA. Here is the formula for CPF. Okay, so this is all given in the textbook. Okay, and as a matter of fact, I'm going to give you a gear design template. The template contains all of these parameters here, so it will save you a tremendous amount of time in terms of your calculation. Okay, yeah. So you don't have to worry an inaccurate entry of a formula. So here's the CPF. Okay, so you have F face width. For different face widths, you use the formula accordingly, right? Yeah. But inside this formula here, okay, there is a small d. That small d, you have to be careful. That d is always pitch diameter for the pinion. Now remember, we're calculating the stress, okay, for both the pinion and the gear, right? Right now. So when you calculate the Km, the d at here, you're not going to change the d. If you calculate pinion, you change it for the dp. You calculate gear. It's not like you calculate for the gear, you change the d. The d here is always the pitch diameter pinion. That's why it's called the proportion of the pinion factor at here. Okay, so d here is the pinion pitch diameter. So you can use the template to help you calculation. You can actually find it out. Of course, it's quite just straightforward. If your Km is bigger, then you will have basically larger sigma. Now, the Km is related to the face width, right? So if you have a larger face width, then you would have a larger Km, basically, okay? And results in the larger stress, actually, okay? Yeah. However, F is on the denominator, right? So if you have a larger face width, you do have a larger Km, but then F is on the denominator, so that at the same time it's also reducing effect, right? The overall effect is actually to reduce so larger face width over effect to reduce the stress. So that's CPF. Okay. For CMA, it's a different formula. Okay, it's A plus BF plus CF squared. A, B, C are taken from this table, okay, based on the different conditions. Open gearing, commercial, precision, extra precision. The definition for each one of these, check out the lecture notes, okay? What exactly does open gearing means, basically. If you have an industry application, a lot of time you see that. You have a big shaft, and there's a huge gear and driving the other one, and they're open in air or something. With a minimum protection, so that typically is called open gear. Okay, yeah. So that basically is CPF and a CMA. So in our case, for this particular case, let's consider the low quality here. Okay, let's consider open gearing. So we can use these numbers from the table. Okay, so you get ABC here, then you can calculate CMA, which is A plus BF plus CF squared, and end up with a 0.28, and then you can calculate CPF, Okay, based on the phase width. Okay, here is the formula for the for the CPM, and that's this value. So overall, then you can produce your Kn, which is 1.322. Okay. So this one here, there's no differentiation. So this is the same value for both pinion and gear. Okay, for both pinion and gear. Yeah. Is that good? Okay. That's Kn. Okay, that's Kn. So next one, let's look at the Kb, which is called rim thickness factor. Okay, rim thickness factor. So let's see what's rim thickness. I have a picture of it here. Okay. So this is the rim thickness. Essentially, let's look at these pictures here. So this is a part of the gear, and here is the gear teeth. Right? Here's the gear teeth. And normally in time, when you manufacture gear, you might want to sometimes, if this is let's say, if this is the this is the gear tooth, right? So sometimes what you do is you remove certain amount of material, right? And basically trying to make it a little bit lighter, and you remove a certain amount of material, and then you have essentially a rim right here, right? This is the part of the rim right here. Okay. So the TR right here is called the rim thickness, and HT right here is the height of the working, basically height, the working depths for the gear tooth. Okay. Yeah. So the rim is a very important part of the gear, because it's basically the part that's supporting the gear teeth, right? It's the base of the gear teeth. Okay, so if the rim is too thin, so there could be one possibility, even if the gear tooth is not fitting, and the rim is already properly fitting before the gear teeth, right? So that's one possibility there. So that's why we need a rim thickness factor Kb at here, okay, for our calculation. The Kb factor, okay, is based on this so-called MB ratio, which is the TR over HT, right? T is rim thickness, HT is the whole depth of the gear tooth, okay? So that's MB. Okay? So to calculate this Kb, you look at the MB value. Okay? If MB is less than this, you use this formula. If MB is greater than that, then Kb just 1.0. So you don't need to make any changes, basically. Okay. Yeah. So in our case, okay, we're gonna assume that our HT, ATR over HT, is greater than 1.2. Okay. If we assume this, then our Kb will be very simply to be taken just as 1 for this particular case. Okay. That's Kb. When you design for a gear, you also need to be careful. If you want to remove certain amount of material and end up the thickness of the rim, so whether you have to take that ratio into consideration or not, that's somewhere you have to be careful. Okay. Okay. So coming back to this equation here, so we have already solved Ko, Kv, Ks, Km, Kb. We have a solve for Kwt. We got the PD, we got the phase width. The only factor here is the J left now, right? It's J here, okay? So let's talk about the J here. Now this one here is called geometry factor, okay? For bending, because this is the symbol inside the bending formula here, inside the bending, right? Yeah. Technically, there is a formula for the J formula here. Okay, we don't need to use the formula. We're going to use our table for calculating the J here. So here's the little bit of story in terms of the J factor, the geometry factor. Now, first of all, this factor here is called J here, right? It's called a J. Now, but this, according to the original Lewis factor, if you look at the Lewis form factor, what's there? It's Y, right? It's the capital Y here. It's capital Y. It's not the J, right? So that's why that's modified. So you see G, there's a Y here, but then Y is modified by dividing another two parameter Kf and Mn at here. Okay. Kf at here. So let's Kf at here is called actually called fatigue stress concentration factor. Okay. So Kf. Okay, if you look at the literature, there is a formula for the Kf. I'll just write it down here. Okay, but really we're not going to use this at all. Okay, here's a stress concentration factor, and the stress concentration refers to the stress concentration at the root location. If this is a gear tooth, so here is the root R. And here is this H here, and here is the T value. Okay, here's the T value. So that's how you get stress concentration at the root location here. Okay, yeah. And R here is the fillet radius, and it's taken as 0.35 over PD, diametral pitch. Okay, so that's how you can calculate the Kf here. And Mn at here is called the stress. Yeah, Mn here is called the load sharing ratio. Okay, so for spur gear, you take it as 1. Okay, for spur gear, you're going to take it as 1. If you're designing for helical gear, okay, it's a little bit complicated, but it's taking as this formula here. Okay, so this is for helical gear. Okay, so the Pn at here. Okay, there's a lot of symbols flying around here. So the Pn at here is called the normal base pitch. So helical gear, there are two circles. One is the normal plane, one is a transverse plane. And this is basically within the normal plane, the pitch value along the base circle. And then this Z value here, it's that length of contact. But this one here is in the transverse plane. Okay, so that's the symbol wise in terms of how J is calculated, here. Okay, but what we're going to do is we're going to use as your figure. I'll show you in the next lecture here. Basically, we use, okay, we don't use the formula. We use a figure, okay, in our textbook, okay, for the J values. Okay, so we'll look at that in the next lecture here. Okay, yeah. All right. So any questions? Okay, all good. Great.